Hey there, everybody. Sorry I can't be with you today. I'm out for a meeting today. So what I'm going to do here is kind of show you how to go through the lab that we're doing today. We're going to call it the StaticsLab. You're going to have three stations that you're going to look at. You're going to look at a simple situation where you have a mass hanging from a single spring scale. You're going to look at a more complicated situation where you have a mass hanging from two spring scales, one of which is horizontal, the other is at an angle. And then the third situation that you're going to do, you're going to have two scales, both of which are at an angle. Our goal here is to do two things. One, show that the forces in each direction are balanced. That's kind of the learning part. And then two, verify that all this stuff about vectors that we've learned actually works by using the values of the spring scales to figure out what the mass of this thing is. And we can actually look at there and see what it is to see if we've kind of gotten close. So let's get started. The first thing that you're going to do is you're going to just read the values on both spring scales. Write this down as you draw a good free body diagram. In fact, let's do that first. I'm going to call this one T1. You can label whichever one you want by whichever number. And it's got a reading of 1 point, let's call that 7 newtons. So that's about 1.7 newtons. I'm going to do the same thing with the second spring scale, which is up here. I'm going to say that this is T2, and it's got a reading of about 2.25. So now that I've done that, I can draw a free body diagram to scale. So you're going to do this on a piece of paper. Make sure you use a good straight edge. You don't have to actually measure this out with centimeters and scale like we did with the other vector lab, but draw it pretty reasonably to scale, just eyeballing it. So T2 is bigger, so I'm going to draw this arrow bigger. Kind of sort of like this. About yay big. And then T1 is going to go to the left. And I'm not going to draw it as big. Maybe something about like that. So I've got T2 and T1, and then the third force that would be acting on it's obviously the weight. And so I'm going to just draw that going straight down. Label that FG kind of like that. The next thing that we need to do is resolve any vectors that are not at right angles into components. So weight going down is good. I don't have to worry about resolving that. T1, which is directly to the left, is good. I don't have to worry about resolving that. So the only vector that I have to resolve is T2. So I'm going to draw components for it. I'm going to use a dashed line for my components. So make that as straight horizontal as we possibly can. And then our vertical component. And I'm going to label those T2, X and T2, Y, just like that. So the thing that I need to measure next in order to get those values for T2Y and T2X is the angle right there. I'm going to call that theta for right now. So here's where you need to actually come up here with a protractor and on this, on the whiteboard, measure what that angle is. So on this one, I get something in the neighborhood of 46 degrees. It's going to be different for every station that we have in the room. Okay? Now that I've got that angle, I can actually resolve these two things and get a value for the two components. So I'm going to use sine to do T2y. Because sine is opposite, T2y is the opposite side, over the hypotenuse, and the hypotenuse is just T2, which is 2.25 newtons. And I can solve for that. Like that. And then I can grab my calculator and actually get a value for that. And so I get something like 1.62 newtons for the y component. I'm going to go ahead and label that over here. 1.62 newtons, and that is T2 comma y. I'm going to do the same thing for T2x, only this time I would use the cosine. And I bet I'm going to get something really close to 1.6 cosine, because that angle is pretty close to being 45. So I get 1.56 newtons. So the next thing we're going to do is we're going to write a net force equation for each direction of motion. What that means is I want to have something that looks like the sum of the forces in the, let's do y over here, y direction equals, and sum of the forces in the x direction equals. So in the y direction, that's vertical, up and down. I'm just going to do something like the y component of T2. Since it's up, I'm going to make that positive. And then the other vertical force is gravity. Since it's going down, I'm going to make that one negative. So I'm just going to write T2y minus the weight, kind of sort of like that. I'm going to do the same thing for the x direction. In the x direction, I've got T2x going to the right. I'm going to make that positive. And then T1 going to the left, so I'm going to make it negative. So I'm going to say minus T1. Now because we know that the mass hanging here is in equilibrium, we know that the sum of the forces has to be 0. Since it's not moving, it's naturally staying at rest, that means that the forces on it are balanced. So our next move is to simply set both those net forces equal to 0. And then I can solve for anything that I'm missing. So just looking at the x side real quick, we can get something like T1 equals T2 comma x. And I want you to show that those are equal. And if we look at the numbers we've gotten, I measured this to be about 1.7 newtons. This is about 1.6 newtons. So the way that I measured them, they're pretty close to being equal. And so that's just kind of a check. Does that work out? If not, then we've either measured something wrong or we've made a mistake in our calculations so far somewhere. So these two forces should be equal. The x component of the tension in string 2 and just T1. The other thing that we're going to do is use this equation, this net force equation, to solve for the weight of this bad boy. And so same kind of thing. Just going to add Fg to both sides. And then I've got T2y to be 1.62 newtons. And so Fg must be 1.62 newtons as well. So in order for the forces to be balanced on this thing, this force and this component of T2 have to be equal, just in opposite directions. In order to find the mass of this guy, there's a new relationship that we need to know. The weight of something, the force of gravity, is equal to its mass in kilograms times g. And you may know g. G has a value on Earth of 9.8 newtons per kilogram. We're going to learn more about that number and why it's special as we go throughout the year. But for right now, we're just going to call that the gravitational field. It tells you how strong Earth's gravity is. And so I've got that number, I've got that number, I can solve for m. And so doing some quick calculating, arithmetic, I'm going to call that 0.17 newtons. That would be kilograms. Got myself all messed up here. Please hold. And so my work looks something like that, and that's the mass that I calculated for this thing. And so if you actually look at this thing, this one says it has a mass of 200 grams. Remember, this is in kilograms, so if I convert that to grams, just multiply by 1,000. That would be 170 grams, which is reasonably close to 200 grams. There's going to be a little bit of error in this stuff, mainly because it's hard to figure out exactly where horizontal is on here. So getting within 30 grams is pretty good. So that's our lab that we're doing today. We're doing two things. We're writing net force equations to see if the forces are actually balanced in the horizontal direction. And then we're using the vertical stuff to actually calculate what the mass of the object is. So the second one that you might do, the one that's straight up and down, that one's going to be simple because there are no horizontal forces. It's just the vertical forces. The third one that you do, where both your strings are at an angle, you're going to have to do the component part for both of them. And so you're going to have both of the tensions having components that you're going to have to resolve before you can do anything else. So you might start with the vertical one, that's the easiest one, then move on to that one, and then save that one for the end. Last friendly reminder, make sure when you're doing all that trig stuff that your calculator is in degree mode. As you're working through this, if you guys have questions, shoot me an email, daniel.marek@gcisd.net. I'll put it on the board for you. Otherwise, hopefully we can work through this, and we'll do some more practice with this when I see you guys on Thursday. Till then, ta-ta.